Thank you for the introduction, and good afternoon. Good morning, actually, for the people that are not as jet-lagged as I am. So diffusion MRI and tractography has brought us macroscale connectomics in the human brain. And of course, this is mostly applied in vivo. And in vivo, we have the great advantage of having whole brain coverage, which we can achieve in clinical large bore systems. But we do suffer from limited resolutions in the order of 1 to 2 millimeter isotropic. Now, ex vivo, we can achieve much higher resolutions, usually in small bore MRI systems or animal systems, preclinical systems, which are in the hundreds of microns. But there we suffer from the drawback that we have very small tissue samples. So the aims of this study was to extend ex vivo diffusion MRI to very large human brain samples. And so the objective study that we took was the entire human occipital lobe. So that's about a 3D field of view of 80 millimeters or 8 centimeter cubic. We wanted to acquire high resolution and high B-value diffusion data. And we have to do that with the challenges in postmortem tissue of low T2s, low diffusivity. And we wanted to investigate tractography of early human visual system projections. So we've already published some work about a year ago on the setup that we use for this, which is a 9.4 Tesla setup using a human bore experimental, so large bore 9.4 Tesla system that we have in Maastricht, and with a custom built coil that you see up there on the right. Now, we like to call that the medium coil because it's not as small as animal coils and it's not as big as a whole head coil, and it can exactly contain cylinders of an 8 centimeter diameter and about 12 centimeters long, and so that is enough to contain an entire human occipital lobe. So we published some anatomical imaging with T2 star weighted GRE with that a year back, and there we could go down to resolutions of 60 micron isotropic. Now, diffusion imaging is quite a bit more challenged in terms of SNR, so we cannot achieve those resolutions, but at least this is a good platform, 9.4 Tesla, and a specifically built coil to jump from. The other thing that we could do at slightly lower resolution, this is at 200 micron isotropic on the anatomical imaging, is to do quantitative T2 star imaging. This is where you get your gradient echo images at different echo times and do a robust fit of an exponential to that, so that you get a quantitative T2 star map, which you can see on the right over there. And I hope you can appreciate that the advantage of this is that the bias fields that you, for instance, get from the receive coil sensitivities that you can see on the images of the left, for instance, you can see that the occipital pole at the bottom is much more bright than the rest of the tissue. They get neutralized, they get absorbed into another map in the quantitative fits, and so you have the advantage of having a bias-free, field-free map, and also of having very exquisite T2 star contrast, which is sensitive indirectly to iron and myelin. And if we take here a slice through the calcarine sulcus, indicated by the yellow arrow here, I hope you can appreciate on the projection that round and about at the white arrow there, you can appreciate the stria of Gennari that I'll indicate with SOG, so we can actually find exactly where V1 begins and ends in our tissue samples. And so we decided to combine this with diffusion imaging. However, diffusion imaging, as I already alluded to, is much more challenging, especially for postmortem tissue and especially at ultra-high fields. And so we had to do quite some pulse sequence engineering to get that done. The standard spin echo sequence that you use in vivo, and also that you would use very easily at 3T, but is already in vivo more difficult at 7T, is not very useful for postmortem tissue because of the short T2 that I mentioned before. So we went to the so-called STEAM sequence, and the STEAM sequence is a sequence of 3 90-degree or pi/2 pulses that you see indicated there, and the second pulse is preceded in blue here, and the third pulse is followed by the diffusion gradients. The big green gradient in the middle is a spoiler gradient that you also need. Now, the trick that you play in the STEAM sequence is that in essence you break the 180-degree refocusing pulse that you have in spin echo apart into the 2 last pulses, and in that way you can make the diffusion time, so that's the delta STE here, much longer and achieve very high diffusion weighting much more quickly. Now, there is also an inherent disadvantage, which is that you only work in the steam echo at the EPI readout train there with half of the signal, but you can compensate this for this particular acquisition, this particular application, with the fact that you can keep your echo time, so you see that indicated with TE here, very short. Now, the final drawback that you have at very high fields of 9.4 is that STEAM sequences, as also spin echo sequences, will suffer from the inhomogeneity of the field, so the inhomogeneity of the flip angle over very large samples. And you see that indicated here on the right for the whole human brain, post-mortem. And you see very large fields of dropouts, very big black holes in the brain. So we modified the standard diffusion STEAM sequence into kT-dSTEAM, as we call it, by replacing the 90-degree global pulses by kT point pulses, which are composite parallel transmission pulses, in order to regain the B1 homogeneity over the whole brain. And I hope you can appreciate on the right there that with the kT-dSTEAM, we get very nice signal, very nice inhomogeneity over the entire human brain, and also then, of course, also then over the entire occipital lobe. So we use this sequence, the kT-dSTEAM, to acquire both excuse me, both very high spatial resolution, 400 micron isotopic. That's about 8-fold 3D higher resolution than was acquired in vivo so far, and it is many times the standard resolution that is acquired in vivo. But we also wanted high B values and a multi-shell acquisition. So we have 4 shells there, ranging from B3000 up to B7000, with varying numbers of directions, so that we have very densely sampled multi-shell scheme there. You can see the raw data on the right there, and you can see that we have quite exquisite contrast between white and gray matter, and also quite exquisite spatial resolution in these scans. So going to the diffusion MRI analysis and starting out with simple diffusion tensor analysis, once we look at a coronal cut, and it's at the blue line in the occipital lobe here, once we go at the diffusion tensor analysis in a coronal cut through the occipital lobe, you can see that we have quite exquisite delineation in the white matter of the different tracts that run through that part of white matter. So we have the third branch of the superior longitudinal fasciculus on top. We have the optical tract and the tapetum and the sagittal stratum very interestingly arranged around the lateral ventricle, as we know they are from neuroanatomy studies, but so far we have lacked the resolution, at least in vivo, to delineate these tracts and their exact position in the white matter with respect to the lateral ventricle. Now, there we go. If we go to the more posterior coronal section that is indicated in red over there, and I'm starting on the left there with the T2 star map, you can see that, and I'm indicating the calcarine sulcus there, and so the rough location of V1 and the stria of Gennari. You can see that right in the middle of white matter there is a much darker spot that actually corresponds more to the right to the green colors of the optical tract. So even within white matter, you can see that there's interesting contrast for the highly myelinated optical tract in the T2 star imaging there. If we go all the way to the right, this is a crossing fiber analysis using the multi-shell data. So this is a ball and stick analysis. You can see that not only can we find the green optical tract there, moving from the lateral geniculus all the way to the calcarine sulcus, but also the fibers that cross through that, such as the 2 smaller U-like fibers that I've indicated with the white arrows there. Now going into the tractography results a little bit more, here you see, and now we're looking at that same more posterior slice from the other side, and I've indicated the calcarine sulcus there, and once again there's the sagittal stratum, the tapetum, the optical tract, and also the branch of the superior longitudinal fasciculus, very nicely delineated in white matter there. Once we try tractography on this, very simple deterministic DTI-based tractography, you can see where all of those tracts that are nicely segregated around the lateral ventricle, the horn of the lateral ventricle in white matter, where they originate. So you see the optical tract and the superior longitudinal fasciculus and the sagittal striatum, which also, by the way, contains a large part of the tapetum on the right there. Now, parcellating these out a bit, at the bottom here, you can see that especially between the optical tract in the middle at the bottom there and the sagittal stratum and the tapetum on the left there, that their different course through white matter also corresponds to a different origin earlier on in the brain. And just focusing on that a little bit more, here's the deterministic streamlining between the optical tractroy in white matter and the stria of Gennari, which we parcellated on the T2 star. You see a very intricate, so viewed from anterior to posterior on the upper left there, and from posterior to anterior from the reverse side in the lower right there, the very interestingly curving tract, the curving pathways of the optical tract towards the calcarine sulcus. Now, A bit more tentatively, we also did some tractography of the sagittal stratum and also the tapetum, where you can see that not only does it course through white matter in a different way next to the lateral ventricle there, but it also terminates very differently in early visual areas, which there's not everything is known about the sagittal stratum and the tapetum connections to early visual areas in human, but at least tentatively it's known that it's much more sparsely connected, especially to V1, and it tends to connect more to the borders of V1 and V2 and the borders of the visual areas at the vertical meridian. And you kind of see that indicated there at the lower right. All right, so where do we want to take this besides analyzing those tracts quite a bit more and a bit more detail and with more advanced tractography technologies? We have high B-values in multi-shell, which means that we can do more sophisticated analysis than just diffusion tensors and ball and sticks. And in particular, we want to go to microstructure analysis such as NODI or CHARMED, and we have some interesting preliminary results there that I cannot show yet. We'd also like to take resolutions like this post-mortem to the whole human brain. And we have already achieved that, where I have to remark though that there we cannot go to as high B-values. We have to trade off field of view, resolution, and B-values. Here we traded off B-values, but we could achieve 400 micron isotropic resolution over the entire post-mortem human brain here at a lower B-value. Furthermore, it would also then, if we look at those trade-offs, be interesting to go to a higher resolution on a single shell for the occipital lobe. And indeed there we've achieved, and you see that on the left here for the occipital lobe, the human occipital lobe, on the right for some test acquisitions on a cat cortex. We've achieved that at 250 micron, and that diffusion data, although experimental and early, looks quite promising. And then finally, it would be very interesting to combine data like this with 3D histology, with optical tissue clearing and light sheet microscopy on the same tissue in order to validate some of these results. Now, with thanking my group and especially Frank Lagos-Fritz, who couldn't be here to present this work because he is at another conference in Paris, and the rest of my collaborators in Maastricht, and my grant givers, and you for your attention. Thank you.